Okay, so we're back for Monday's lecture. I want to take a moment or two to pick up where I left off. So the big theorem that I talked about at the very end of last time was if G is a P group, the order of G is P to the n is greater than 1, P is a prime. The first big interesting theorem about P groups is that in this case G admits a normal subgroup. Okay, so of course every group admits normal subgroups. Weight, right, the identity, and G itself, so that can't be interesting. So what's the interesting content? The interesting content is that n isn't that. So n is squeezed between identity and G, and furthermore, all the subgroups of n are also normal. Okay, and this basically followed from the fact that G had a very large center. Right, so one thing we proved before this was that if G is a P group, then its center contains non-identity elements. And so basically, you either take n to be the center in this case, or if G itself happens to be a billion, the center is the whole thing, right, then n, when you think about it, right, n is supposed to not be G, so you can't take n to be the center in that case, but because of the classification of finite abelian groups, it's very easy to find a subgroup, you know, with these nice properties. And of course, every subgroup of an abelian group is normal, so there's no harm in assuming normality there. Okay, that's basically exactly this proof I just said. Let me say that normal subgroups are extremely important. So they're exactly the subgroups that when you quotient out by them, you get a group. Right? So the quotient by a normal subgroup is a group again. It's not just a coset space with an action, although it is that. It actually has the structure of multiplication on itself. Okay, so let me write down a corollary now of this theorem. So corollary. So again, let order of G equal P to the n. And let's say n is greater than or equal 1. This theorem actually makes sense for n equals 1. So then there's a sequence of subgroups. So then there is a sequence of subgroups of G. So I'm going to call them, following Goodman here, E, which is called G0. That's contained in, so what's where it equals, contained in G1, contained in G2, contained in, and G is G sub n. Okay, so there are n plus one of these. They start at 0 and they end at n. 0 is E, Gn is G, such that the size of G to the k is P to the k, and G to the k is normal in G for all k. Right, so what's happening here is you can squeeze one in between the identity element and G. You can squeeze a bunch of subgroups, and they are as big within each one of these subgroups is as big within the next one as possible. So the order of G to the k is P to the k. So this means, right? So this means that the order of G to the k mod G to the k minus 1. What is that? That's P to the k divided by P to the k minus 1, right? Which is P for all k, right? So of course all of these groups are P groups. Their size divides powers of P. So how closely can you squeeze two P groups together? Like, what's the biggest size one P group could be within another? And the answer is, if the quotient has size P, that's as big as you can get, right? Because the quotient is always going to have size some multiple or power of P, and P is the smallest one. That's not trivial, right? So this is saying that there's a sequence of subgroups that is maximal. You can't squeeze any further subgroups in between any of these subgroups, because all of these quotients are just cyclic groups of order P. They just have size P, which is as small a size as you could get. Okay, so this sequence is special. It's not unique necessarily, but it's maximal. It's the largest one you could get. If G is abelian, by the way, this follows again from our elementary divisor theorem. if you just look at the form of that. If you have for instance, a cyclic subgroup Z mod P to the K, then you can, if you think about it for a minute, you can see, okay, well, the subgroup generated by P in there has size P to the K minus 1, and the quotient is Z mod P. And then you can keep going. Inside there, there's a subgroup. Inside the subgroup generated by P, you have P squared, P cubed, etc. So it's that kind of sequence. So if you find this statement confusing, I would encourage you to write down G as Z mod P to the N, or Z mod P cross Z mod P, or something, and start looking. You can find these sequences. They're not, as I said, they're not unique, but it's not hard to imagine. It's not hard to imagine how to make them. All right, so let's prove this. So this goes by induction on N. By induction. So when N equals 1, I'll just say there's nothing, then this is nothing to say. Right, when N is 1, this just says that you have E and you have G. Okay, and they're normal. So we don't need to assume anything on N. Even when N is 1, the theorem is true, and it's actually obviously true. So if so suppose proved for all m less than n, and find, now as in the previous corollary, we find E contained in N contained in G not equal size of N is P to the M less than P to the N, right? So okay, so I didn't say this. So let N be greater than 1 for this. So when N equals 1, that's the base case of the induction, and it's trivial. Now let N be greater than 1, and suppose, this says suppose proved for all M less than N. So suppose that induction holds, then by the previous lemma, what I call it, corollary probably, theorem, you can find a normal subgroup like this, right? Such that N is normal in G, such that N is normal all N prime in N are normal. Okay, so it's a normal subgroup with, lots of normality happening. Right, if I say, right, it's a normal subgroup, and all of its subgroups are still normal, so it's extremely normal. I don't know if there's a word for that. Mathematicians sometimes like to call things very whatever, so we could think of it as being very normal, but I don't think that's like an official terminology. Okay, so by induction, now N is a P group, right? The order of N is something that divides P to the M, so it's P to the N, excuse me, so it's therefore P to the M. So by induction, we can call N to be G sub M, and there exists E, is G0 contained in Gm. Right, so what is GM? GM is GM. GM is N, right? It has size P to the M, so just name it that, right? And then so now we have to fill in the rest, right? How do we go from GM up to G? Well, now you take the quotient group, G mod GM. This is a group, right? So this is a group of size P to the N minus M, which is also strictly less than P to the N, right? So we know the size of this. We know by induction that this group admits a filtration by subgroups exactly in the same way. So there's a sequence of subgroups of that. So there exists, how to call it, so G0 prime, which is E, inside G1 prime, inside Gn minus M prime, which is G mod Gm. Right, so there exists a sequence like that, and then what do? For each one of these subgroups, we just pull it back to G. So we let G. Okay, I probably misnumbered these. So what I should call this is, I should really call this. Okay, so here's what I'm going to do. I'm going to cheat a little bit here, and I'm going to say this should really be called GM. This should be called G1 plus M, and this should be called Gn prime. Okay, so I'm doing the induction, except now I'm cleverly relabeling everything so that the sizes match what I want them to be, and I set Gi to be G in G such that the image of G in G mod GM is inside Gi prime. Right, in other words, I take the inverse image. Right, so in other words, i.e. if pi GM is the quotient map, then we set Gi equals pi inverse Gi prime. Right? Okay, and because this GM is a normal subgroup, it's easy to verify that this is a map of this is a group, this is a map of groups. So these inverse images are subgroups, and what's their size? Well, the size of the quotient group plus however big the size of the kernel of the map is, and the kernel of the map is just GM, P to the M. So it's very easy to verify that these have the correct properties. So I'm just going to put a box. So I'll leave it as a kind of exercise for you guys to make sure that's true. It's not difficult at all to prove. Okay, so all right, yeah. So let's give it. Yeah. So that's a very nice. So that's a very nice filtration that exists. All right. So let's do some real structure theory. So we're now going to move to groups which are not prime power, but such that P divides the order of G. So we now want to move. So now you want just P divides order of G. Right. So now take any finite group and suppose that it is right. So it's a size is a number, and so you can do a prime factorization. Suppose that P is some prime that divides that order. We want to say something about the structure of G. Well, of course, it's a much more complicated problem, because now instead of just working with groups of prime power order, we're working with any arbitrary finite group, which is obviously crazy, right? It's much more complicated. But in fact, it turns out that if you fix a prime, you can look at sort of subgroups of prime power order, or subgroups whose such that G mod that thing has prime power order, etc., etc. It turns out that you can actually say some interesting things. So you want to extend these results to just P divides the order of G, and the first thing is a nice theorem, a famous theorem called Cauchy's theorem in group theory. So suppose P divides G, exactly the same assumption. I wrote it twice. I don't know why. Then G has an element of order P. Okay, of course, we know the converse is true, right? If G has an element of order P, then it contains a cyclic subgroup of size P, right? What does it mean to have order P? It means that that element generates a subgroup, which is just a cyclic group of, just Z mod P. So this is saying now, and then in that case, P must divide G, right? Because the order of a subgroup always divides the order of the group. This is the converse. This is saying, now just suppose that you have a group and suppose that P is some prime dividing its size, dividing into its size, then in fact you can find an element of exact order P. So this is much less obvious. So let's give this proof. The book gives a very slick proof. If you look in other algebra textbooks, you can find different ones. But I like this. I like this proof very much. So use group actions again. Now this time on the, well, you'll see. So you set X to be the set of collections of elements in G, such that, so what does it look like? A1 through AP, such that AI is in G, and A1, AP is E. So you take a set X, and what is it? It's the set of P tuples of elements of G, such that their whole product is just E, right? So in this case, this is the same as saying that AP is A1 AP minus 1 inverse. So this tells us that the cardinality of x is cardinality of g to the p minus 1 power, right? Because I can freely choose my first 1 through p minus 1 elements in G. I can pick them to be anything. They can be different, they can be the same, it doesn't matter. That gives me order of G to the p minus 1, that number. And then once I've chosen those first p minus 1, then AP is completely determined, right? You just take the product, whatever it is, and you take the inverse. Okay, so we file that away. Right, and then the next thing to note is you can permute. So next note, that's A1 to AP in X implies AP A1 AP minus 1 in X, right? Why? This is because A1 AP minus 1 equals AP inverse, right? So this tells us that when I multiply the first p minus 1, the assumption is that when you then multiply that by AP, you get E, but that's exactly saying it's the inverse, right? So this implies that AP times A1 through A P minus 2, well, say it this way, times AP minus 1 is E as well. Yeah, let's put it that way. I don't need P minus 2, right? So, right, if this is true, if the product of this AP A1 through AP minus 1 is AP inverse, then when you multiply it by AP on the other side, A1 through AP minus 1, you get E, right? So just by basic group theory, if you're an inverse, you're a one-sided, you're automatically a two-sided inverse. Right, once I have an inverse in groups, it's an inverse on both sides. Okay, so, in other words, I can act on elements of X by just rotating through. So therefore, Z mod PZ acts on X, sending I to right? So I need to tell you for I and any element in X, so I has to go to a bijection on X. So I goes to what bijection? The bijection A1 AP goes to, and now the point is I'm going to rotate over I places, right? So now A1 is going to be in the ith spot. I think I should say I plus first spot, right? Because 1 is going to act by taking A1 over to there. Yeah, so A1 is in the I plus first spot, and we have AP in the ith spot, AP minus 1 in the I minus first spot, all the way down to AP minus I. So this is, right? And again, when I is 1, that's your first rotation. So this is minus I plus 1, excuse me. Great. Good. Up through AP, and then this is A1, AI, P minus I. Okay, great. Okay, so that's what it is. So it's, in other words, rotate I places. Right, and of course this is the composition of rotate one place I times, and since rotate one place preserves the set, rotate I places preserves the set. When I is P, this just does nothing, right? This takes A1 through AP to A1 through AP. Okay, so wait a minute. That doesn't seem right. That would be A0. So this should be P minus I plus 1. Hold on, what? Oh yeah, sorry, A1 through AP, and there's nothing there. Yes, it's correct. Okay, great. So this is rotate I places. Great, perfect. And it's really an action of that. All right, beautiful. Okay, so now let's look at this action. It has orbits. Every element is either, as Goodman says, a fixed point, or it has an orbit of size exactly p, right? So each orbit has size which divides p. So each orbit, if O in X is an orbit, right? The orbit is the quotient of the group, right? It's G mod, so the stabilizer. And the size of O is either P or 1, right? Because this is Z mod P. So either you are the stabilizer is 0 and you're of size P, or the stabilizer is the whole thing and you're of size 1. Those are the only numbers that divide P, so that has to be true. And so this implies that X is a union of fixed points under Z mod P and orbits of size P. So X is the union of fixed points under this action and orbits of size P. Okay, so now why do we actually care about this? Well, remember, what are we looking for? We're looking for an element of order P. Okay, so if you so the point is that if you so those are going to come from essentially from fixed points of the action, right? What is a fixed point of this action? It's something that whenever I take any rotation, I get the same thing. So that means that I look like A1, 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 right? Right? Each way of rotating the elements around gives the same element, so they all have to be equal. But then also A is A to the P minus 1. All right, so we'll do it out in a minute. So the point is the inverse. So or maybe even better to say is that A is E. So a fixed point is actually going to give you an element of size, of order exactly P. Okay, I'll prove that rigorously in a second. So let's show why it matters. So all right. So the size of X, again here following Goodman's notation, is N plus Kp, where N is number of fixed points, right? I take the orbit decomposition. Each orbit is either a singleton set or it's a set of size P. So I union them all up. I get N fixed points, and then I get K orbits of size P, and so the size of X is N plus Kp. Okay, so now this number N, of course, is greater than or equal to 1, or maybe I'll say this in a different way. So the next claim is that the size of X, being G to the P minus 1, is divisible by P. So size of X, we computed that a few minutes ago. That's G to the P minus 1, and so P divides. P divides size of X, right? So P divides size of X, P divides Kp clearly, and so together these things imply that P divides N. Okay, and so if P divides N, this implies that either N is 0 or N is strictly positive, since E is fixed. This is certainly fixed under the action. We have that N is greater than or equal to 1. Right, there's a fixed point, so N is at least one element. So N is at least 1, and so this implies that in fact N is greater than or equal to P. And P divides N, and N is at least 1. So there is a fixed point that's not E. So therefore, there exists a fixed point A. This is what I was saying a minute ago. Why does the fixed point look like this? Because I'm taking my A1 through AP and I'm rotating them over, and I'm always getting the same answer. Right? So if you pause for a second, that means A1 is AP, AP is AP minus 1, AP minus 1 is AP minus 2. Right? You just keep doing it, and you see that all the elements are equal. So fixed point has to look like this: A, and of course, A times A, which is A to the P, equals E, implies that the order of A is exactly P. But that's it. There's a non-identity element which is exact order P, and that is that is actually really the claim. Okay, so I think I'm gonna in the spirit of these videos being 25 to 30 minutes, I'm gonna stop soon. I want to at least state the first Sealed theorem. So next lecture, which maybe I'll try to post tomorrow, we want to prove the following. If P is prime and P to the n divides G, here now n to be greater than or equal 1, then there exists what you call it, H inside G, a subgroup, order of H is exactly P to the n. Okay, and this is the beginning of what are called the Sylow theorems, which kind of classify these subgroups of size whose size is a power of P. So well, classifies is stronger, but we'll talk about what they do over the next couple lectures. But notice that this is a direct generalization. When n is 1, this is a subgroup of size P, but all groups of size P are cyclic, so that just means there's an element of order P. So that's exactly what we just did up here using this clever X trick. So next time we'll induct on that n, and extend the argument to this case. Okay, it's a little complicated and the video is getting long, so I won't do it now. I'll do it in my next short video, and we'll explain how the induction on n works and what's going on there, and then I'll state the Sylow theorems and sketch out their proofs and kind of interesting things there. Okay, all right, we're off to a good start this week. I will see you guys soon.